welcome to Anne, and you can start with your presentation and with his topic, the basic mechanism of security in 5G, 6G. Welcome, Anne.
Thank you, Paola, for the introduction, and good. I would say good morning for you over there. It's already evening or almost evening here in Belgium. So I'm gonna see if I can upload my presentation. Let's see if that works. Okay, do you see my slides?
Yes, we see it's okay, we can see yours.
Okay. Good. So we were supposed to start in 8 minutes. Do I already start or do I wait? I'm not sure if others are still going to come or not.
See, it's okay. You can start because now the audience is there, and we start a little bit before because for some proofs, but now the people is here for your.
Okay, you're all following. You're maybe all following. Oh, sorry. Please.
So sorry. Maybe if I can just jump in. Hi, Anne. It's Bart here. There will be also time for questions, so we have allocated enough time. Maybe I would suggest at the end of each presentation, because we have it's a hybrid event, so we have quite a lot of people online, and I can see they are still joining. I will be monitoring also the YouTube channel in case there are any questions there. And also, I think we have some students and staff in person in UDLA. So perhaps, Paola, you can monitor on this side. If there's any human in-person questions, you can take them, and we can take a look at the chat. And at the end of each presentation, we can ask the presenters if there's anything coming up. So yeah, that's just my 2 cents here in terms of organization of the event.
Okay, so we keep the questions for the end.
Yes.
Yeah.
Okay. Okay, good. So then I suppose I start. So I think everything regarding the introduction has been already said. So I just want to add that if you have questions regarding this talk or other things related to this talk, don't hesitate to contact me. So you can find here the email address on the site. Okay, good. So for the talk of today, so I will start with some history. Then I shortly explain the 5G specific architecture, security threats related to this architecture, and finally I will end with some conclusions, key takeaways. So we'll start with a bit of history. Before we come to the 6th generation, there have been several generations passed. So the capabilities in each of these generations, they drastically increased. But not only the capabilities, because as you can see here on the slide, also the different types of attackers and the capabilities of these attackers also increased over time. And now what we are going to do is quickly go over each of these different generations and let's discuss them a bit more with a focus on security related aspects. So we start with the 1st generation, and the 1st generation of cellular systems were limited to voice services, analog, and which was analog communication. So, and with respect to security, there was in fact totally no explicit security measures taken into account because of 2 reasons mainly. First, it was not so easy to do on analog communication. And secondly, security was not at all popular outside the military world. And we are speaking here the 70s, 80s. And so as a consequence, all communication was open. And so all types of attacks going from eavesdropping, data privacy breaches, authentication issues, everything that you can imagine was possible. So it must have been a dream for hackers during that time. but luckily they were not so active then. And then 10 years more or less later, we are in the 90s, and we have the second generation that was developed. And now, for the first time, it was not anymore analog communication, but it was digital communication. It's called now the GSM, or the Global System for Mobile Communication, and that became the most widespread use standard. Regarding security, there were 4 priorities. So anonymity, authentication, protection, signal protection, and user data protection. And unfortunately, besides these 4 priorities, which were more or less established, there were still several issues. So first of all, the network operator was not able to do the verification of was able to do the verification of the authentication, but not the other way around. So it was completely possible that there was a fake operator because the user was not able to authenticate or to verify that. So we had only unilateral authentication. Man-in-the-middle attacks were perfectly possible. The whole system was also built, there were the 90s, on the principle of security by obscurity, meaning that the details of the security mechanisms that were inherently used, because in order to have user data protection, there were encryption mechanisms used, but the details of these algorithms, they were not published, and so they had to be revealed by means of reverse engineering. The drawback is it takes a bit more time, but it was feasible, and the community were able to derive the cryptographic algorithms, and they were called A51 and RC4, and both of them were very badly broken. So although user data protection was established, it wasn't really established because the underlying cryptographic mechanisms were very weak. And then the third thing the third disadvantage of issue was that tracking was possible. So the privacy of the identity was only protected by means of a pseudonym. And this pseudonym was fixed for each particular user during the whole lifetime of the device. So if you were at some moment possible to make the link between a pseudonym and the real identity, which you might maybe do in case of a very important person, then you can completely track the whole behavior of that person. And then, of course, we also have the denial of service attacks. And actually, that's an issue that you will see in each and every generation. It becomes a bit more difficult, but it's not something that you can solve only by means of cryptographic operations. So, and then, the last main issue was that everything was fixed. So all security that was used in it, all the different algorithms, implementation, protocols, everything was fixed. So it was not possible to upgrade it at a later moment. So that was the second generation. Then we come around 2000, so the third generation that was on the market. We had at the time higher data rates than 2G, limited video streaming, also video calls became possible, and there was a huge improvement in data rate compared to 2G, which clearly, nothing of video was possible. From a security point of view, important to mention is that in 3G, now we speak about the so-called ACA protocol. It's called the Authentication and Key Agreement Protocol. It's the same mechanism that we had in 2G with some improvements on top of it, but now it got a formal name of an ACA protocol. So, like I said, structure-wise, it was similar, but it's a bit stronger. So what we have, for instance, is that we have still this anonymity track, but only anonymity. So they use the pseudonyms, but they were just a little bit more frequently updated. So it's still limited, so the traceability attacks are still there. Then there are still issues with weak encryption algorithms, although the previous ones, A51, that was replaced by Kasumi, that also turned out to be weak. And so then what we also have was denial of service, of course, is that the cloning of SIM cards was a big issue at that time, and that followed from the fact that the physical security protection of the data, which should be stored in tamper-proof memory, was not strong enough. So key and identity data could be easily retrieved from the card and then stored in another card in order to, in fact, impersonate the user. Okay, good. Then we go to the fourth generation. So in 2010, it's in fact what we have actually still today in some of the cases, is 4G or LTE, long-term evolution advanced network, in which video streaming, video calls become much more feasible, and we have a very huge improvement in data rates. So the fourth generation supports also the third generation partnership project, 3GPP, which is a collaboration between telecommunication standards organizations that communication standards organizations that develop protocols and specifications for mobile telecommunication systems. So overall, while 4G is not directly linked or based on 3G technology, they inherit and extend the access security mechanisms that were defined by 3GPP. It's also important to know that this technology of 4G is interoperable and backward compatible with 3G. Now, regarding security innovations, one of them is the introduction of a new ACA, Authentication and Key Agreement Protocol, which is also the one that come later to it, similar in 5G, but some small little things, changes made. So important to mention is that it also supports the non-3GPP technologies such as Wi-Fi, Bluetooth, and other local area network and personal area network technologies that can communicate with 4G networks through specific mechanisms and interfaces. And furthermore, important security feature is that for the first time, there is a cryptographic network separator such that the spreading of attacks can be limited. And so it basically means that the user equipment can authenticate to the serving network, the roaming in fact, and that is based on the approval of the home network. So serving network is really completely different, physically different from the home network, while before it was like one integrated part. Still, we have denial and distributed denial of service attacks, and then there are also issues with the ACA protocol, but I will come to that later on too. Good, and then around 2010, it's the great breakthrough of the IoT, Internet of Things. These are the small constrained devices that are connected to the internet. And there were many advanced developments in different domains, and going from sensors to applications. And also it resulted, in fact, into additional challenges for the communication network to be able to support them. And that's also one of the reasons, in fact, that we come into the 5G era, which we have today at 2020. And that's it's not like just a simple incremental improvement, like bit 3G versus 4G. In 5G, we have drastic change. And if you can see here the different features on this figure, there is a drastic, so 4G is the dark blue, and then the light blue is here the 5G. Then you can see that there are drastic improvements with each of these different features. So, and there is a huge market also around this 5G, which makes it very attractive. I know the project is about 6G, but in fact, we are still, at least in Europe, still in the phase of rolling out 5G, which is not at its optimal usage of capabilities. So it's still important to also talk about 5G. And in addition, many of the things that will be used in 6G will build on top of 5G. We will look at the different issues that are still present here in 5G and not solved in hopefully will be solved then in the 6th generation. Okay, now we will delve a bit more into the 5G specific architecture before we can actually speak about the security threats. So as you can see, we have these drastic improvements with respect to data rate, bandwidth, etc. But then the question is how to obtain that. And there are different reasons. So first of all, there are quite some reasons that are related to improvements with respect to radio communication. So first thing is here new spectrum. As 5G utilizes a broader range of frequency bands, including higher frequency bands like millimeter waves, and they offer wider bandwidths, enable faster data rates, and support the deployment of new services. And then the second thing is that there were also advancements with respect to antenna technologies that include beamforming and massive MIMO, multiple inputs, multiple outputs. And it's this beamforming that allows for more focused and efficient signal transmission, while the massive MIMO improves the overall network capacity and coverage. The third improvement is related to a flexible frame design that allows to adapt and configure the structure of communication frames based on specific requirements of different services and use cases. So examples of this is that you can have a variable slot duration, dynamic time division, duplexing, etc. Good. Then fourth important thing is about the multi-connectivity in 5G, which refers to the capability of a user device, a user equipment also called, to simultaneously connect to multiple cells or base stations within the same or different frequency bands. And what we can also do is that it supports diverse types of traffic within the same frame. And so we can have ultra reliable, low latency communication and at the same time enhance mobile broadband in a single frame. And that enhances, of course, the reliability and the performance and the overall user experience. And then finally, very important is, of course, that it's built upon the idea of a distributed architecture, which is a fundamental design principle, and that aims to provide improved flexibility, scalability, and efficiency in all the network operations. Okay, good. But in addition to the radio, also the whole 5G architecture became softwareized. And it's also, we are not going to focus security with respect to radio aspects, but more on this 5G core architecture. It became softwareized. It didn't become softwareized from the first step. So it's in fact 4 phases that it had to go through. And in the first phase, we have the virtualization phase, which refers to the implementation of network function virtualization. And that involves transforming traditional network functions, which were previously implemented in dedicated hardware, into software-based functions running on virtualized infrastructure. With the main goal to increase flexibility, scalability, and efficiency of the network operation. Then we have the second phase, which is about service migration, and that refers to the process of transitioning existing services and applications from legacy infrastructure to the newly virtualized environment, the one that we have created in phase 1. And then we have phase 3 is the orchestration, which is a critical element in a virtualized environment, and it involves the automated coordination and management of various network functions and services. So this orchestration that streamlines then also the deployment, the scaling, and the management of these virtualized resources that we have from phase 1, and so optimizes the network performance and resource utilization. And then finally, the last phase before coming there, that's then the service network automation that ensures that the entire network operates seamlessly and adapts dynamically to changing demands. So automation mechanisms help them to orchestrate and optimize resources to deliver a wider range of services. So this service network automation, there are two important aspects in that. That's network slicing and the MEC, or the multi-access edge computing. And so network slicing, that is allows the creation of multiple virtualized isolated network slices within one physical network infrastructure, with the idea that every slice can be tailored to specific service requirements such as latency, high bandwidth, massive device connectivity, and so on. So, and you all know what a MEC is. MEC is with the idea that you bring computational capabilities closer to the end users, such that latency is reduced. So it's the opposite of the cloud computing. Good. So just to summarize, we have 4 main pillars in this 5G architecture. That's the SDN, software-defined networking, the network function virtualization, NFV, the multi-access edge computing is MEC, and the network slicing. So, and that's also what we're going to do. We have in the next part, we will discuss security with respect to the 5G ACA, but also with respect to each of these 4 components. So one thing I also wanted to add, so you see here on the top, the right bottom of the slide. So all is the softwareized approach is all follow the principle. And nowadays it's kind of very trendy to say SIT and DevOps. And these are 2 frameworks. SIT is continuous integration and deployment. These are practices that are commonly used in software development and deployment in order to streamline processes. And the SIT is a development practice where developers regularly integrate their code changes into a shared repository. And every new integration that triggers also automated build and testing processes to detect and address integration errors early. So on the other hand, and you have DevOps, that's more cultural and organizational approach that promotes then the collaboration between, on the one hand, the develop team, and on the other hand, the operation team. Okay, good. So up to here, the general idea of the main points of the infrastructure. So now we go to the 5G specific security threats. So first, what I wanted to discuss are the pre-5G security aspects. So that's the security of the previous generations that are in fact also present in 4G. And so we have discussed security of 4G before when we discussed about the history. Well, here, this is in fact everything that is related to the ACA protocol, authentication and key agreement protocol. As I said, there were some issues with that in 4G that were not completely solved. We'll find them back in 5G. They are a bit harder, some of them due to the new antenna technologies, but you cannot say that the threat is gone completely, especially not for attackers, hackers with more advanced technology, because their capabilities also increase. So what are the different threats or issues that we still need to take attention for? So first of all, or the mobile-ware attacks, which are mostly the denial of service attacks, the botnet attacks, the advanced persistent threats, and they can still pose threats to 5G networks. These attacks have typically the ambition to disrupt the services, compromise the network resources, or gain unauthorized access during a weak moment. So it's impossible to solve this type of attack solely by having a good cryptographic ACA protocol. That's really something that you have to solve with additional tricks like intrusion detection techniques, anomaly mechanisms, and so on. So, but yeah. That can happen. Another thing are the physical layer attacks. So you can still have signal jamming, interference, eavesdropping, man-in-the-middle attacks, and they remain concerns, although they will not be able to break the privacy because you don't have the keys required for that. But it can cause some inconsistencies that are not very practical. Then roaming frauds and IP hijacking attacks. So 5G already enhances these security mechanisms for roaming, but there might always be a risk of fraudulent activities due to IP hijacking. And so here again, continuous monitoring of your network traffic are essential to mitigate these threats. We can have attacks via the non-3GPP networks because, as I said before, this 5G can coexist with non-3GPP, like, for instance, Wi-Fi, WiMAX, wireless local area networks, fixed networks. And so it's possible that if an attacker is able to break into these networks, it's then interoperable with 5G, that it can then also break into your 5G network. So therefore, you need to make sure that also security measures are in place also in these non-3GPP networks. We can have a lack of perfect for what is there is shortcomings then actually from a cryptographic point of view in the 5G ACA. That's the perfect forward secrecy attack, meaning that if a hacker to find the or to retrieve the private long-term key material of either the core and the home network or the user, then it will be able to break all previous session keys and to derive, if it has stored, of course, all the data that has been sent before, to also retrieve all this data. So that's a very big issue in the current generation 5G ACA protocols, this lack of perfect forward secrecy. And then the last one, of course, is that the mechanism 5G ACA is using public key cryptography, although limited, only actually in order to protect the privacy the identity of the user. So, and you all know that with the current generation of public key cryptography, so in this case it's elliptic curve cryptography, that once we have a quantum computer, that it will also be broken. So, and then also, you could say that the symmetric key algorithms, that the security strength is not enough, but that's easy to solve. The more problematic part is that for the hiding of the identity, where public ECC is used, elliptic curve cryptography is used, that is vulnerable for the so-called store now and encrypt later attacks. So if you want to protect the identity of your communication for the case that there will be a quantum computer, I don't know, in 5-10 years, then it would be good to update your 5G ACA protocol to such a post-quantum resistant protocol. The only problem is that it's not so straightforward to do that, because for the resistant post-quantum protocols, they might be more or less computational operational efficient, but the problem is that they cost a lot with respect to communication. So they have a very high bandwidth cost. So it's not that easy to simply replace them. Okay, so these are like the issues to take into account when it comes to the ACA protocol. Then next we have the software-defined network tracks. And so as you can see here at the architecture, you can also see that there are different threat vectors at different places of your architecture. So first of all, there is point one, place one, the centralized controller, which you can also see as a potential single point of attack and failure. So if your controller is compromised, then an attacker could gain control over the entire network, leading to unauthorized access, data manipulation, service disruption, and so on. So, but then we can also have attacks on, we call that the southbound interface. So that means positions 2, 5, and 6. So between the controller and the data forwarding devices. So, and they, mainly the threats there is that it becomes vulnerable for availability attacks, and because they can be blocked, integrity breaks or integrity vulnerabilities and performance attacks. So, and then also we have attacks on the northbound interface. That means between the controller and the application plane. So if you look at the architecture, that's positions 3 and 4. Then what we have there is mainly insecure application programming interfaces that may be susceptible to attacks such as injection, spoofing, or unauthorized data access. And there can also be malicious applications with some built-in vulnerabilities. Good. Next, so at the end, second main pillar was the NFV and network function virtualization, which was the concept of transforming hardware-based network functions like a router, a switch, and so on, into software or virtual functions. And so here, the goal is again to separate the network functions from the underlying dedicated hardware such that they can run on standard hardware. So we see again the architecture, or most important architecture of this network function virtualization. And what you can see here is that the central part is this, you see here threat vector 1 is the MANO, or the management and orchestration entity. And this is again the, if you want, a single point of attack in this, in this context of NFV threats. So if you, as an attacker, are able to break in here, then you can do quite a lot. So you can do malicious misconfigurations, excessive logging, you can leak the logs, you can make sure that you do a privilege escalation such that you have access to other parts in the architecture that are not allowed. You can steal data from ephemeral storage and so on. Good. So, and besides the MANO, we have these other threat vectors. So the second part is the attacks at the virtual network functions, where here is mainly can cause interoperability issues, denial of services, attacks, software flaws. We can have virtual machine escape, virtual network function manipulation, and so on. Then we can have on number 3 attacks on the virtual machine. So these are then the virtual migration, a problem of lack of isolation. Kind of have here scheduler attacks, but that also comes then in attacks on the hypervisor, where here you can do manipulation of your virtual machine. You can break the isolation. You can also exhaust, of course, the hypervisor's kind of denial of service attack, exceed the log troubleshooting failure, and so on. And then finally, we have the attacks on the physical hardware, and here it's mainly physical attacks, really disk failure, code execution on the physical host, state manipulation, resource interference attack, input-output, or CPU, etc. Good. Then we are now at the third pillar, multi-access edge computing. You see again the architecture with the different threat vectors. So if we go over it, first of all, we have the vulnerabilities at the level of the user equipment. User equipment can be IoT devices, mobile phones, drones, cars, etc. So here mainly it's denial of service attacks that allow disruption of the architecture, that add fake data to the network, for instance. Then we can have attacks on the communication channels. There are quite a lot of communication channels. So you see here number 2 is between the user device and base station. We have number 4 is between base stations among each other, base station and the core network. And then 7 is between, it's the internet, in fact, between third-party cloud services, the core, and the MAC server. So here on the communication channel, it's mostly about eavesdropping, Sybil attacks, spoofing, relay, denial of service attacks, enabling man-in-the-middle attacks, and so on. And then, of course, we have number 3, which is then the edge network, because it's the MAC. And here it's about components that are, these are the components in the edge network that launch the storage and provision the services for the MAC subscribers. So attack vectors then mainly target the virtualization technologies, such as virtual machine manipulation, virtual machine escape. Also, like we've seen before, a virtual network function, location shift, domain name system amplification, security, log troubleshooting, and so on. And then finally, we have the attacks on the core network, and so that's number 5 and 6. So here it's a bit the same as what we have in the MAC, but then one layer higher. So even here is the most critical part if this is attacked, and that can be, for instance, by insecure APIs of your application, authentication or authorization issues, again, denial of service attacks, malicious injections, and the less isolation you have, the higher the impact is, of course, on the whole network. Okay, and then finally, the last pillar is the slicing. And here, network slicing is the separation of multiple virtual networks that operate on the same physical hardware for different application services or purposes. So we can have like 4 main threats. So it's possible that there will be side channel attacks across slices due to different security protocols or policies in different slices. It's possible to have impersonation attacks against a network sliced instance within an operator network. We can, of course, have denial of service attacks to other slices by exhausting network resources. And then finally, it's possible that information can be stolen from slices if you have a user equipment that is attached to several slices. So, and there is not a proper isolation between both of them. Okay, now that we've seen an overview of all these security threats, what are the general security solutions? I keep them general, and I also combine them for these 4 main pillars, so the SDN, NFV, MAC, and slicing, because basically it always comes to the same principles. So you need to have strong authentication and authorization for every single entry points or every single element entity in your network. And that can be SDN controllers, switches, NFVs, MAC slices, managers, other components. So it's very important that strict access controls are enforced based on roles and responsibilities to limit the privileges of authorized users. Then it's clear that communication should be secure, preferably end-to-end or hop by hop, and security of communication that requires that you use secure and well-established cryptographic protocols, TLS, IPsec, etc., and also which have secure cryptographic algorithms included. So because then you can prevent eavesdropping attacks and unauthorized access to sensitive information. Another important point is isolation and network segmentation. So if you want to reduce the attack surface, you need to work with micro segmentation and isolate critical assets in order to limit the movement of an attack in your network. Fourth thing is, of course, do regular software updates and patches. So that's clear that you need to keep the devices up to date with the latest security patches, and that software need to be regularly updated to address vulnerabilities that are known in the meantime and to reduce the risk of exploitation. This also includes like proper security monitoring and logging, so to implement real-time monitoring of traffic and events. So nowadays you have a lot of AI tools that allow you to do that. The logging mechanisms, they are kind of essential in order to analyze data and signs of malicious activity. And so you can set up alerts for suspicious behavior to enable incident response. And these are the so-called IDPS, intrusion detection, and IDPS is the intrusion prevention attack systems. What else we can say is that, of course, security audits, it's something that is, if your company is complying to regulations like ISO 27001, they also enforce you to install regularly security audits, so they can also help you to overcome or to detect attacks. Another thing is like what they often call supply chain security, is to ensure that the vendor with who you work has appropriate security assurance. So that's, for instance, if you want to be compliant with NIS2, it's one of the very important criteria that you have to address. And then also in each and every security policy, education and training is seen as a very crucial security feature to take into account. Okay, good. So I think we are here at the end of the call of the presentation. I can end with some conclusions or key takeaways. So although maybe first to say that this network softwareization that we have shown to come to the 5G really core architecture, and that brought many advantages like fast deployments, update of security mechanisms, centralized security controls, and granular policy management, there are still several new security issues that require additional care. We have the fact that 5G has open architecture, and especially now, since also support approaches like ORAN, where we have multiple vendors and third parties to contribute to network components like radio units, distributed units. This openness that increases the attack surface, and so introduces also many more points for malicious actors, including supply chain attacks, where we have compromised hardware of software that can come from untrusted vendors and that can be exploited. So the fact is also that when we shift to this softwareized 5G, and then it also requires operators and developers to have deep expertise in securing virtualized environments, and that is completely or significantly different from traditional hardware-centric networks. And so it's this lack of widespread know-how among staff that can sometimes lead to misconfigurations, human errors, unpatched vulnerabilities, and sometimes also inadequate security policies. Third thing is that we can have these software-defined systems in 5G, such as virtualized baseband units or control planes. They are more susceptible to hacking because they rely on code that can be reverse engineered, exploited via zero-day vulnerabilities, or attacked through malware. So this hardware. And then what we had before, these hardware-based systems, they often had physical temper resistant, and they were much harder to modify remotely. So that's something to take into account. What we also have is that this virtualization that eliminates traditional network perimeters. So the physical firewalls that we had before, it relies now on software-defined boundaries, which are less tangible and harder to secure. So without physical security, like for instance, locked server rooms, these virtualized elements are vulnerable to remote attacks, especially if hosted in multi-tenant cloud environments. And then finally, we have a softwareization approach that enables a rapid deployment of virtualized network functions to meet the demands for all types of traffic. But the fact is that this speed can often also bypass thorough security testing, and so potentially introduce vulnerabilities that attackers can exploit before patches are available. So, and as a consequence, to conclude, what we have explained in this presentation is in fact a link between security threats and architectures that are related to these new approaches and the SDN and NFV, MAC, and slices. And it's important to take into account that proper protection of each of these components is required. And you know, what they say is that security is as strong as the weakest link. So now we have here much more links included, so it's also each and every link that needs proper protection. So what we didn't address in here, but there are many new technologies besides the standard approaches of access control monitoring that will enhance the security management. That includes distributed ledger technology, super interesting in the context of 5G, 6G. Artificial intelligence, machine learning, also super interesting. We'll see more about that. We have physical layers protection techniques. It's a domain in itself, and I touched a bit upon the quantum technology, but here it goes much more further with quantum key distribution and so on. And also, I want to just end with the fact that privacy is also an important challenge to take into account. It's a presentation on its own, what I didn't do here. So this was really just a basic focus on security with respect to 5G architecture. So that was the presentation. So thank you very much for listening. And if you have any questions, then I'm very happy to address your questions.
Thank you very much, Professor Anne. I have here some questions that some students have sent me. How do the security mechanisms in 5G differ fundamentally from those envisioned for 6G?
Well, the the thing is that the difference between 5G and 6G is that 6G is much more relying on artificial intelligence and machine learning mechanisms. So 5G is putting the foundation, but really the automation, not only automation with respect to orchestration and so on, but also with respect to security management is really something that will be addressed in the next generation. And second important part is that post-quantum technology is something that will very likely be included in 6G, which is currently not at all present in 5G. So these are, like, I think, two main aspects that differ between 5G and 6G.
Thank you. Is here another question? What role do hardware components play in ensuring end-to-end security in future wireless systems?
Yeah, so hardware security, then mostly it's related to trusted execution environments, secure hardware, tamper-proof storage, and so on. So, of course, this will be very important. It's always been very important. So, and because you don't want an attacker to be able to have access to critical components, not only of the device of your IP, but also on the keys that are stored in there. So hardware security is a very important domain. And that's not limited to 6G. Of course, this is in 5G or even the previous generations. It's super important.
Okay, thank you. I think here is another question. Who sent me this? Albert. How can emerging technologies such as artificial intelligence, blockchain, quantum computing, and trust execution environments especially contribute to overcoming the key challenges of security orchestration in 5G and V5G networks?
Yes, so distributed ledger technology. So why can they use this first of all to ensure transparency for the management of the network, auditability, the logging, automation. These things can all be put on the distributed ledger. It's a decentralized approach, which is also following the idea of 5G and 6G. So from that point of view, it has certainly an added value. There's lots of literature on that. It's like the advantages of DLT in 5G or in 6G. It's super interesting. If you're interested, I can refer you to that. So artificial intelligence and machine learning, that's on two sides. On the one hand, we can apply artificial intelligence and machine learning to improve the security, and that's meaning then to improve your tools for intrusion detection and prevention, anomaly detection, and so on. But on the other hand, it's also challenging to make sure that your artificial intelligence is secure on itself. So meaning that it uses that the data on which it's based is not fake data, that you have the protection against all these type adversarial AI attacks, etc. So that's a double sword, they call it. So AI for security, but security for AI. So physical layer protection and the trusted execution environments are important to make sure that if your attacker somehow has physical access to devices, because we work in a decentralized environment, it's possible to have more entry points, physical entry points also, to protect you against that. And then, quantum is cleared. So, to make sure that as I explained to you then for this 5G ACA protocol that we have now, it's relying on traditional cryptographic primitives which are not resistant to quantum computers. So in order to overcome your protection, you have to find a solution in that. That's it.
Thank you so much.
Hola. If it's okay,
Sí.
can I jump in with one question?
Yeah. Okay. Here is another question. Go ahead.
Okay. So because I want to utilize this platform as well, because it's very international meeting. As you can see, we're between Europe and Latin America. So there may be a lot of people, especially from your side, interested in the research that is ongoing in the European countries. And as you know, we do have 5G deployed in most countries. The 6G is what we are involved in. So there are a lot of people that will be giving the presentations that are currently involved in defining the 6G throughout a lot of different European projects. So we have been, Anne has covered a lot of, from the beginning to the history of the generations until now. And then there's beyond this. She has talked about the security challenges, but challenges in general. So I just want to throw in here that in Europe, there's still a lot of open research happening, and there's still a lot of opportunities. So we look into, things like in the physical layer, we look into reflective intelligence services. There were some questions about TEEs. So we do have companies, for example, like NEC, that is looking into the trusted execution environments. People do work in let's say, the architecture itself. So there's a lot of work going on in zero touch management. And as you know, we have seen already the shift from 4G to 5G, where it wasn't only a shift in terms of a better throughput and a better speed, essentially. We also have seen the change in the whole paradigm, like distribution of the network, multi-vendor environments. And we also see this 5G to 6G. It's not just 5G on steroids, meaning 5G with AI capabilities, but it's also either further disorganization of the network. So coming to the point, there is a lot of research in 5G and 6G happening in Europe, and a lot of opportunities. And in your group, what is it that you are focusing on? Because perhaps we can build also some connections with the attendees. Like, what's your main focus in your group?
Yeah, so the main focus that we do is on the authentication and key agreement protocols. So in fact, on the cryptographic security protocols that are there between the different components. So that's our expertise. Also, we worked on distributed ledger technologies because it's closely related to the security protocols. That also involves quantum. I mean, developing the protocols nowadays is quantum resistance is quite hot to include in your protocols. And then also when it comes to physical layer protection, it's things that we look at, but mainly from the point of integration into our protocols, not like designing our own trusted execution environments, but really using it as a starting point for defining our protocols. So, but we are not like specialists in this AI based techniques, like what I know that other groups are, working very hard on it.
Yes, perfect. So, the post quantum crypto, all the research groups that look into different lightweight protocols. Also, this is still a very hot topic in research and industry. And I think I mentioned just now the lightweight. Everyone is now looking into energy efficiency aspect of the solutions that are being developed for 5G or beyond 5G. And in fact, any proposal for the project that you put in now in this current environment has to be covering some aspect of energy efficiency and sustainability also. So if there is any researchers interested in that, I do recommend linking up with some EU partners that may have some opportunities to work together. Yeah, just taking this opportunity to link up the presenters also with everyone else that's here. Back to you, Paola.
Yeah, thank you so much. Now, I don't know if we have Bart more time for more questions, or we continue with Chamita.
I think we can continue with Chamita, and also there will be details shared of each presenter at the end. So maybe we can limit to 3-4 questions maximum. And then if there is anything more that people want to follow up with, they can follow up directly with. Well, hopefully Anne will not receive 25,000 emails now with a lot of questions, but we're always happy to, take a few more.
Yeah, so I just put my email address here. If there are any questions that you'd still like to ask, then you can send them to me. So thank you very much, and I wish you a very interesting day. So here we are getting more to the evening. So thank you very much for listening to me, and yeah, let's stay in touch if you're interested, and thank you very much. Bye.
Yeah, thank you, Anne. Thank you very much. We continue our second with Chamita. I will introduce him.
Hi.
Hi. Yeah. Chamita, the title is Security in the IoT Ecosystem and Next Generation Network. I will introduce to Chamita. Before to continue, I want to say that at the end of all this presentation, we will have a QR for the registration, please. Decirles a todos que al final de las charlas nosotros tendremos un código QR para que se puedan registrar la asistencia. ¿Sí? Yeah, sorry. I will introduce to Dr. Chamita de Alwis, is a senior lecturer at the School of Computer Science and Technology, Faculty of Creative Arts, Technologies and Science in University of Bedfordshire. He is also a senior member of the Institute of Electrical and Electronics Engineer at SMIEEE and a fellow of the Higher Education Academy. He also offers consultants service in areas related to mobile networks and cybersecurity. Chamita holds a Bachelor in Electronic and Telecommunication Engineering with first-class honors from the University of Moratuwa and PhD in Electronic Engineering from the University of Surrey in UK. Chamita's researcher interests focus on cutting-edge areas such as artificial intelligence security, cybersecurity, network security, 5G, 6G technologies, and blockchain. He has successfully secured numerous competitive research grants and actively contributes to several high-impact research projects. Thank you. Now we will continue with Dr. Chamita, please.
Hi, Paola. We had some sort of a time mishap, but hopefully that's fine now. And I'll that's fine. I think, but I'll focus more on 6G security as a whole area. So I saw that the previous presentation by Anne, it also focuses on the paradigm shift between from 1G to 6G. So I'll try to sort of have minimal overlap. Well, you might ask why 6G and we already have 5G. So the obvious answers are like yes, the expansion of IoT, massive availability of small data, which is sort of like increasing, and we get a lot of self-sustaining networks and sort of like the integration of communications, computing, control, localization, sensing. zero energy IoT, and many advancements of communication technologies, gadget-free communication. And surprisingly, the increasing elderly population is also one fact, because they will demand more and more ambient assisted living, and all other emerging technologies and applications. So I will not sort of like go through the previous mobile networks and generations, because I saw the previous slides and they were covering them in detail. So if you look at 6G, from 5G, actually, we are moving towards a very different paradigm shift. So as Bart also mentioned, it's not just 5G on steroids or 5G with a boost of AI. It's actually very wide. It has a very wider scope. So this is why, like, we envisage peak data rates in the range of terabits per second, and extremely low end-to-end delays ranging from like 0.1 milliseconds, very low processing delays, and reliability and availability in the range of 7 nines, and also extremely large connection density devices, and extremely high energy efficiency, spectral efficiency, and very high mobility, because we are also looking at catering to very new applications like space and deep sea tourism. And also we'll see a lot of new applications like UOVs, holographic telepresence. So this first figure shows actually the paradigm shift between 4G and 5G towards 6G. So we can see that it's a significant leap, that this is what is envisaged with 6G, and we envisage to see 6G networks by 2030. So this is the envisaged timeline to see 6G, and we will have a lot of new applications ranging from collaborative robots or cobots, UAV-based mobility, intelligent healthcare, smart grid 2.0. So if we look at all those things, what we will see is that this new paradigm, which is very different or very comprehensive, or that is very distributed. So all these things will increase the attack surfaces. All these things will maybe open up for new threats. So this is why we should be really serious, and we should really look at 6G security aspects. So this is something that many researchers, including me, are focusing on. So if you look at the paradigm shift of security towards 6G, so from analog voice, which we had from 1G, where networks were prone to physical attacks and stuff, and then came 2G, so we had sort of like authentication issues, and then with 3G we had sort of IP traffic security issues, viruses, spyware, and with 4G, sort of like networks started to get these advanced persistent threats, DDoS attacks, malicious apps. And with 5G, now we sort of experience things like cyber warfare, and sort of attacking to critical infrastructure. And we in news, we also start to see like some critical infrastructure breaking because of cyber attacks. And with 6G, actually, this attack landscape will grow. And we can actually categorize the attacks, or the security threat landscape of 6G into three main categories. So one can be pre-6G related security issues. So those are issues that are inherent to sort of like pre-6G technologies, or already sort of testing local 5G or 6G networks. So they can also relate to some security and privacy issues related to IoT that's moving towards IoE. And we can also look at the other category, which is security threats of 6G architecture. So actually, we will see a lot of new things ranging from tiny cells, mesh networks, multi-connectivity, sub-networks, RAN co-convergence, zero-touch networks. So these will sort of introduce some new threats. And the other area is the security threats of 6G technologies. So these technologies are the ones that sort of power 6G architecture, 6G technology, 6G services, and 6G applications. So they may range from artificial intelligence, machine learning, blockchain, quantum computing, visible light communication. So one example for security issues that might come from pre-6G technologies is we envisage network slicing also to be a key part of beyond 5G networks. So this part of our research sort of focused on finding what are the security issues related to network slicing, and we sort of explored and found that there are many areas where there are security issues related to network slicing, ranging from life cycle security of different network slices, inter-slice security, intra-slice security, slice broker related security, SLA management, ZSM or zero touch network security, and network security related trust and privacy. So these will sort of escalate, or these will towards trickle down to beyond 5G networks, including 6G also. And if we look at the technologies that power beyond 5G communication networks or 6G communication networks, so these like AI, DLTs such as blockchain and quantum communication and terahertz and visible light communication. So those are some sort of predominant technologies that power this, or that will power 6G networks. And AI, well, this is something like a very a hot topic these days. So it's AI, yes, it has its marvels. However, it is also susceptible, sort of vulnerable to some security threats, such as model poisoning attacks, evasion attacks, machine learning related API-based attacks, infrastructure attacks, or compromising of AI frameworks. And if you look at DLTs such as blockchain, we can see like Eclipse attacks, or sort of like 51% attacks, or end user vulnerabilities, software vulnerabilities. And when we look at quantum communication, so this a completely a new area that is sort of that scientists are working very hard to realize. So still, like, there are a lot of vulnerabilities there, or like areas which are still not understood, such as probably quantum entanglement, how it works, and sort of how to do multicast and broadcast with quantum computing. So with that, like, there can be quantum cloning attacks, quantum collision attacks, and with terahertz communication, we can have access control attacks, eavesdropping, same with VLC, and jamming with VLC. So you can see that there are still areas that we need to work on. However, these are actively these are active research areas. So there are many research work on these areas. Oh, there are a lot of opportunities to work in these areas. And if you look at 6G, we also sort of understand 6G to have a lot of AI and intelligence built in. So if you look at the 6G architecture, well, there are different ways of presenting 6G architecture. So this is one way of looking at it, such as we can look at the intelligent sensing layer, which will sort of be connected to all these devices and IoT devices and so on and so forth. And then it will be connected to the edge layer, which will have data centers and edge servers, and then it will connect to the intelligent control layer that will have the centralized cloud, and then it can be connected to different applications. So all these layers actually also have also come with some new security threats. So if you look at the intelligent sensing layer, we can see that there can be cryptographic systems that are not strong enough, maybe with quantum computing, or maybe there can be rogues or compromised IoT devices, data theft, eavesdropping. And if you look at the intelligent edge layer, there can be sort of like physical security threats, DDoS attacks, man-in-the-middle attacks, and then there can be attacks on the edge-based different microservices there, and then there can be attacks on different machine learning models. And if you look at the intelligent control layer, we can see that there can be attacks on software-defined networking controllers, interfaces, virtual machines, hypervisors, and information theft or DOS attacks. And even if you look at the application layer, still there are data privacy issues. Maybe like there's absence of machine ethics when it comes to automation, and there can still be 51% attacks on blockchain, because we expect that the blockchain will be a key enabler or key component of many 6G applications. And if you look at 6G application requirements, so many applications that we discussed before, ranging from connected autonomous vehicles, smart grid, Industry 5.0, intelligent healthcare, digital twin. So all these things, if you look at these requirements, you can see that security is a paramount. So say, for instance, if you look at intelligent healthcare, you can see that we really need ethical AI security, and then we need high privacy, scalable IoT data security. And if you look at digital twins, still we have like IoT data security, AI security, secure communication. So if you look at this, we can see that one of the key requirements or key demands of this 6G application is actually having a secure environment that will ensure security and privacy. So if we sort of go into detail, we can see that these applications, these 6G applications actually have very diverse security requirements. And if you look at their security and implantation challenges, that is also quite diverse. Say, for instance, if you look at UAV-based mobility, that will have sort of security requirements, like the critical ones might be extremely low latency, extreme scalability, zero-touch security, and security via the edge. However, if you look at something like Industry 5.0, that has different security requirements. So maybe that has, in addition to the ones that we discussed before, it might have need proactive security. So maybe zero-touch security to operate like in an autonomous fashion. And the challenges are also quite diverse. Say, for instance, like energy efficiency is a big challenge for UAV-based mobility. However, like if you look at something like Smart Grid 2.0, so it has different challenges, like physical tampering, terrorist attacks, because these sort of deal with so tampering a Smart Grid 2.0 network might sort of impact the energy grid of a whole country. So what can we do to resolve these issues? So this is what we really need to work on and focus on. So there are different solutions that scientists are working on, researchers are working on. So I will sort of focus on some of them, which I think are prominent. And so one such thing is actually like, so before going to that, actually, when it comes to AI security, so we actually look at AI security in sort of two different ways, because like we need to secure AI, and then we can use AI for security. Say, for instance, like if we look at different autonomous systems, we can use federated learning, deep learning, and privacy preserving machine learning. So these ways we can actually use AI for security. And then if we consider like security for AI, we can see that this way we can actually consider like ethics, and we can build resilient models, and we can actually build trustworthy models. And actually, like AI is sort of so that's one of the prominent solutions that we are looking at in sort of enabling as one of the potential solutions for 6G security. So considering the nature of AI, actually, like it is also considered as a double-edged sword. So it can be used for different purposes. Say, for instance, AI in 6G can be an enabler of security, enabler of technological enabler. It can also act as a defender of 6G networks. But not only that, it can actually sort of be an offender, so it can also make it a target, right? So, so if you look at how adversaries act, we can see that they can use AI models to sort of like steal data. They can detect vulnerabilities. They can automate their tasks. They can launch different attacks using for AI models. They can do some things like poisoning data. They can attack to these model poisoning in different ways, in the learning phase, inference phase. So it's it can AI can be looked as a threat. And on the other hand, AI is actually an enabler, because it sort of enables a lot of 6G related tasks, such as automating different network service and management and stuff. However, if you look at in the security aspects, we can see that it also helps to sort of have security in different parts of 6G, maybe like for intelligent authentication, authorization, or maybe for anomaly detection with AI. So actually this AI and 6G landscape is a very sort of broad one. So it's there are many knowns, there are many unknowns. So that's why it's a very hot topic, a very hot research topic at the moment. So there are many people who are working in AI and 6G security. And another sort of interesting area in AI and 6G security is explainable AI, because when people use AI for different tasks, like they start to question, okay, so how do they make the decisions? The decisions that they make, are they sort of ethical? Like, what's the decision making process? Can we sort of look at the process and see if it follows the essential steps? Or can we defend this in the in a court? So in such a scenario, we need to know, we need to break down the basic steps of how these things are working. So that's why explainable AI is, and also like explainable AI for 6G is also becoming another hot topic, another hot research topic. So so they sort of start to decipher these AI models to see like what's happening, where, and how things are happening, and what are the technologies being used inside. Like so this is also another interesting area when it comes to 6G security. And actually we can apply this XAI into 6G security in across the 6G networks, like starting from where it's sort of starting from devices, IoT devices, or any other device that people use to get connected to 6G networks. And also we can use this XAI in the core or the network edge, and we can also use this XAI in different services and also applications. So this will allow researchers and also like operators and also governments to sort of understand how these networks, how these technologies work, to decipher them, to make them more efficient, to make them more secure, and ensure that they sort of align with any regulations or any other policies of different governments or countries or operators. The other technology that is really interesting when it comes to 6G security is blockchain. So blockchain has a lot of advantages, and blockchain actually is used for many parts or many aspects in 6G. However, still, if you look at this diagram, you can see that there are a lot of attacks that can happen to blockchainized 6G platforms, starting from like poisoning attacks, or like sort of looking at different sort of Sybil attacks or like spoofing attacks. So these kind of things actually like make using blockchain in 6G also a bit challenging. However, like this is also another research area. So you can see that most of the technologies that we are using for 6G security, so still this is a growing area. So like people or researchers are still exploring, okay, we can use this technology, that's fine. It has proven itself as a very prominent technology, very capable technology. However, still there are some remaining challenges. So actually this is why these areas are very good for researchers to sort of explore and then resolve these issues. And actually blockchain has a role in enhancing 6G security in multiple aspects. So if you look at zero energy IoT, that can sort of increase the efficiency of these kind of activities while securing it. So you can see that it's throughout 6G networks. So this is why like blockchain and 6G security is a very key research area. And another interesting area is quantum computing with 6G security. So this is a very interesting topic. We actually recently also published a survey article on this, which might appear online soon. So here, actually, there are many areas that such as like maybe post-quantum safe cryptography, and what kind of quantum-based attacks can happen, and quantum key distribution, how we can sort of implement these things, and how can we build quantum resistant network hardware, and along with that, how can we sort of do machine learning in a quantum computing environment to make it more efficient and safe, and how can we sort of do quantum assisted communication. So all these are the aspects that are currently being researched on and developed on towards attempting to develop a quantum safe 6G communication platform. So like some researchers believe that there are still a lot to happen to have quantum computing by 2030 and to make it a key technology by 2030. However, like even with 5G, we saw that many key technologies sort of started to appear maybe like after 4 or 5 years of 5G being launched. So some scientists believe that that's the same case with quantum computing. However, only time will tell. So like there are many research work going on in this area. And even when it comes to physical layer security, well, we will have a lot of new challenges, because currently researchers are looking at many new things, like such as intelligent surfaces, how or like some people call them reconfigurable intelligent surfaces, how they will work. So these are actually like a very hot research topics. So people are working on realizing sort of efficient and sustainable ways of implementing intelligent surfaces. And using visible light communication is another very interesting area. So that some believe that we can replace Wi-Fi and those kind of technologies, where you sort of connect different devices, maybe like maybe inside stores you can have some devices that might connect with the Wi-Fi or something like that. However, like when it comes to visible light communication, we see that tampering visible light communication is very easy. Even a small torch can do that. So what are the measures against that? So these are also some areas that people try to research on, and some completely new areas such as like molecular communication. So these are very hot topics, and these areas try to sort of merge the developments of biological sciences with communication technologies. And actually, like that's also a very new area to me, even how this molecular communication can happen, and how the security of that molecular communication will be, because that requires a lot of knowledge that we should bring from biological sciences towards these areas, and maybe like physics. So if you look at 6G security, so considering all the aspects that we discussed, we can actually sort of derive some KPIs that we need to have have a strong 6G security. So like maybe we can look at protection level. So like different applications will need different protection levels based on the sensitivity, the time to respond. So that can be sort of like if something happens, how much time or what's the time scale that we need to sort of look at in responding to that, the coverage of the security aspects, and how what's the autonomicity level, and then the robustness of this AI, and security AI model convergence time, security function chain round trip time, and the cost to deploy. So these are some of the KPIs that's being identified when looking at 6G security. So different applications based on their requirements may have different KPI requirements for these measures. And actually, that's the end. I think I try to finish within my 30 minutes. Paula?
See, tell me, we have some questions.
Yes, that's fine. That's fine.
Okay. Where is from this guy? Yeah, thank you, Dr. Jamita. Here we have some questions in the chat and also internally. How do you envision the integration of blockchain enhancing security within the IoT ecosystem, especially in the context of the next generation network like 6G?
Yes. So, well, it's this is also a really interesting research area. At the moment, even like if you look at how people mine Bitcoin and use Bitcoin, we can see that there are different mining nodes and there are different other nodes that use these kind of services. So I think the same. So as per my knowledge, or as per the knowledge that we currently have, I think like the same sort of structure will evolve. So there'll be a lot of devices that will be using these kind of blockchainized systems. However, still there can be a lot of mining nodes in the edge, and they will do the blockchain mining. They'll do the consensus and all those kind of behind the scenes activities. And I think it will make a lot of these IoT devices operate in a large network in a very trustworthy manner, because at the moment the problem is sometimes like okay, how can we make this trustworthy, because there are different devices operating in different ways. How can we ensure the security? So like these are areas about blockchainized IoT and blockchainized 6G network try to address. I hope I answered the question.
Thank you. Someone is having some questions, because here I have one more internally. I don't know someone. Yeah. What are the main cybersecurity challenges that IoT device will face as they become more embedded in critical infrastructure supported by 5G and 6G networks?
Can you repeat the question, please?
Yeah. What are the main cybersecurity challenges that IoT devices will face as they become more embedded in critical infrastructure supported by 5G and 6G networks?
Okay, so well, the thing with IoT is I think like the same characteristics that we observe at the moment, because there are devices that will need a very sort of like they'll need to preserve their power, so they have limited battery capacity, and then they sort of have very less sort of processing capabilities. So I think these will evolve, but with time we envisage that edge computing will sort of empower IoT devices to take better decisions, to have more computational power, but still the same challenges that we already experience will sort of evolve. However, like when it comes to critical infrastructure, so one of the research that we focused on is actually smart grids. So smart grid 2.0. So we sort of envisage that because at the moment we see that there's a lot of initiatives to implant this renewable energy, such as maybe solar power and stuff for different houses. So then each of these things also integrate a lot of IoT devices, and they become a part of a very large infrastructure that powers maybe countries. So in those things, actually, like it becomes more. So maybe a country can become more vulnerable, because this is sort of like connecting the power grid with the IoT network. So the existing challenges will sort of evolve. However, on the other hand, there'll be a lot of security or AI-based security starting from the edge. So that is what we envisage. And also we sort of are currently looking at many new physical layer security aspects that sort of will empower these IoT devices, even with less processing capability, to have better security. So all these are very state-of-the-art research themes. And hopefully by the time that we see 6G, we will see that these technologies being realized.
This is very interesting, and if I may just add on top of this, this reminds me of the general problem we had with the IoT devices. So if you begin with the invention of the IoT, which is let's say some years back, we started to see the problems of data. So we started to produce a lot of data. And then we had the cloud, so we were sending everything to the cloud, and we realized that we need to do some intermediate aggregation of data and some data processing. So that's why we introduced, let's say, fog computing. Right, and now people even talk about mist computing, and essentially mid layers between the edge devices and the cloud. With security, we also have a similar problem, because not only we have to collect all the data from those devices, in the meantime, we also have to collect additional data like telemetry, battery, authentication data that needs to be processed. So this is why, and this is coming back to my previous also comment with Anne, we need this lightweight mechanism. So at the moment, we send aggregated data to, let's say, intrusion detection system, and we try to figure out if maybe one of our edge devices was attacked or not. We need to do this intermediate processing, but it costs. It costs a lot in terms of energy and the processing power. So that's why there are many researchers that are looking into this lightweight security enhancement of these edge devices first. Then they try to secure the fog, and then eventually, before even it gets into, let's say, some kind of intrusion detection systems, we need to do a lot of pre-processing in terms of the security before, but the cost is enormous, right? If you have an edge device that can last a year, and it produces on one battery, and it produces some data every couple of minutes or maybe every couple of seconds, and then you add a security function on top of this that isn't really optimized, you may reduce the battery power to something like few days or even few hours if you need to run some kind of models on this. So this is a big research problem, and again, I invite people to look into this because lightweight security solutions are needed. So yeah, just on top of what Chamita said, I think this is quite interesting problem.
And what to add to that, actually, like with IoT devices, we start to see the demand for small data. So like we are quite familiar with big data, where we use data that we collected for a very long time probably, and then to see the statistical patterns. However, when it comes to small data, sort of we try to collect data that is relevant for the time, so that is very recent maybe, so and then to make decisions on that. So for that, we need to collect this data, process this data. Say one example is maybe like the operation of a machine. So we need to collect this data from different sensors across the machine, and to see like if there's if we envisage a failure, how it will happen, and to collect this data. So in these kind of things, collecting this data and sort of coordinating different IoT devices and connecting them. So this is a very big challenge, and then it also opens up new security challenges, because there's very less time to verify this data, to sort of check this data. There can be some model poisoning attacks. So actually, like a lightweight and powerful security sort of algorithms and technologies, it's a paramount.
Yes, and we realized this during the deployment of 5G. And then obviously everything that you said requires ultra low latency, and the latency that we had with 5G was not so bad, but for this almost real-time applications, when instant feedback is needed and instant data is required, then we need ultra low latency. So this is what we try to also do with 6G, but of course the management of all of this is not straightforward. That's why we still don't have an official design and architecture of 6G. This is what projects like HexaX2 and similar projects are trying to to do. So I think there are a lot of people that put their efforts into defining what 6G is based on this is one of the requirements we just gave: ultra low latency, instantaneous data, near real time communication. So yeah, definitely a lot of opportunities there as well, and challenges, I guess, that come with it.
Okay, thank you very much, Chamita and Bart, for the discussion. Now, Henry will be our next speaker. I don't know if it is ready. Henry?
Hi, everyone. I'm ready here.
Yeah, I will introduce him. Yeah. Well, Henry will talk about... Sorry. Second. Yeah. Henry will talk about the enhancing security at the physical layer of wireless system application in code domain node. I will introduce to Henry. Yeah, Dr. Henry Ramiro Carvajal received his bachelor degree in electronics and telecommunication engineering from the Universidad de Las Américas, Ecuador, in 2009, graduating in the top student among all technical and engineering programs. He later earned his master and PhD degrees in electrical engineering from the School of Electrical and Computer Engineering at the University of Campinas, Brazil, in 2014 and 2018, respectively. In 2018, he served as director of the Technology Transfer Division at the Secretariat of Higher Education, Science, Technology, and Innovation, CENESID, in Ecuador. He obtained the HCIA 5G certification from Huawei in 2020 and has been a senior member of the IEEE. Since 2022. Since 2024, he has served as Vice Chair of the IEEE Communication Society, Ecuador section. Dr. Carvajal is currently a faculty researcher at the Universidad de Las Américas, UDLA, Ecuador. He is the author of more than 50 high-impact journal publications and actively participates as reviewer and technical program committee member for various international conferences and journals. His research interests include digital communication, wireless system, orthogonal and non-orthogonal multiple access, multiple user detection, MIMO, reconfigurable intelligent surfaces, fluid antenna system, physical layer security, machine learning, and emerging technologies for 5G and beyond 5G networks. Continue, Dr. Carvajal, please.
Okay, thank you, Paola. So just one question. Can you see my screen?
Sí, yes. Sí.
Okay. Good afternoon here in Ecuador. Good evening in Europe. I will extend my gratitude to the organizers of this insert training event, in this occasion hosted by Universidad de Las Américas. So I commend this initiative for creating an international event. It is a space for collaborative environment focused on addressing the critical challenge of security and privacy in next wireless communication systems. So for me, it's an honor to be part of this effort here. Okay, I'm going to talk to you about a technique called non-orthogonal multiple access, which is related with Internet of Things. This is a very interesting topic. in the previous presentation, Chamita and Bart talked about the challenges that implies ensure security for Internet of Things devices. So my presentation is related in this line or in this topic. So for beginning, let me talk about a little bit about 6G communications. So we know that mobile networks have mostly focused on commercial aspects in their development over the years. So, however, the push for 6G wireless communications, that is sometimes called as 6G humanity, aims to prioritize a more human-centered approach. So the goal of 6G is not just technological advancement, but also contributing to sustainable goals. In addition, addressing societal challenges and supporting economic growth. So the emphasis is on making technology more inclusive and human-oriented, benefiting various industries and seeking for positive changes. For this purpose, we require technological advancements, and in this context, we can observe here that centimeter positioning, artificial intelligence, terahertz technologies, and cyber physical security are interesting technologies for ensuring security in future 6G communications. Okay, in this figure, we can see that physical layer security, we observe here like phy security. This is a novel technology for 6G physical layer. In particular, this figure obtained from the 6G flagship indicates that this technology has not so high uncertainty, but a considerable impact on wireless networks, okay? So in a general way, a wireless network may have some limitations, for instance, open wireless access medium, limited bandwidth, system complexity, limited power, limited processing capacity. So for this reason, conventional approaches to ensure security in wireless network may prove insufficient in certain emerging scenarios. So mainly due to the low computational capabilities of some devices. So in particular, I'm talking about Internet of Things devices, okay? Well, so what is the idea behind physical layer security techniques? Here in the slide, you can see we have a transmitter named as Alice, a legitimate receiver named as Bob, and an untrusted receiver or an eavesdropper, which is named as if. So physical layer security techniques aim to guarantee reliability for the legitimate link. This is the link between Alice and Bob, and secrecy for the wiretap channel. So in other words, the link between Alice and Eve, okay? So when reliability, we mean that Bob can decode the message transmitted by Alice without error. This is theoretical, this is perfect reliability. And by secrecy, we mean that Eve does not obtain information from the message transmitted from Alice to Bob. In this case, we have perfect secrecy. In practice, in real system, this doesn't occur at all. But this is the main idea. So we have different metrics in this area. For instance, secrecy outage probability, which is the probability that the channel capacity of the legitimate link minus the capacity of the wiretap channel falls below a threshold. Or even we also have the error probability, where the aim is for this probability to be extremely high for the eavesdropper, okay? Well, this is the aim of physical layer security. So now I'm going to give a brief introduction about non-orthogonal multiple access. This is a very interesting technique that wants to guarantee a lot of devices connecting to the same base station. This is one of the aims of 5G or 6G when we want to ensure massive connectivity, okay? So here we have first orthogonal multiple access. Specifically, orthogonal multiple access is used in 4G, in the first releases of 5G. And the idea here is that there is no interference among users within the same cell. The idea here is that one user or one symbol is transmitted in one subcarrier, okay? So in the other side, we have non-orthogonal multiple access. Specifically, there is interference among users within the same cell, and the interference can be mitigated using multi-user detectors at the receivers. Obviously, they are more complex than the receivers that are used in orthogonal multiple access. Okay, so the idea of this non-orthogonal multiple access is to ensure communications for 1,000 devices per cubic meter. Okay, that is one of the KPIs in 6G communication. And for this reason, non-orthogonal multiple access is an interesting option for future wireless systems and for IoT networks. Okay, so the idea here, you can see that I have the information for 1 or 2 users transmitted over the same subcarrier. So we have interference. We have 2 different proposals for non-orthogonal multiple access. The first of them is power domain non-orthogonal multiple access, and the second one is co-domain multiple access. The idea is to divide or to separate the information of the same users transmitting in the same subcarrier using the power domain or the code domain. Okay. Well, among the various co-domain non-orthogonal multiple access techniques proposed in the literature, here we have a sparse code multiple access. This is a very interesting technique. This technique was proposed in this paper here in this conference in 2013. Basically, the concept is that different bit strings are directly assigned code words that belong to different books of multidimensional codes. It's a little bit difficult to understand this, but the idea is to create, using a Cartesian product, the idea is to create mother constellations that are multidimensional constellations that are obtained from the Cartesian product of QEN or rotated QEN constellations. Okay, well, what are the advantages of this technique? First of all, sparse code multiple access allows the system to be overloaded. What it means? It means that the number of users that are served by the system can be greater than the number of subcarriers in the system. Okay, this means that the system is overloaded. In addition, we have that we can employ a multi-user detector called based on belief propagation in the receiver, which is also based on the message passing algorithm in the receiver. This is a nearly optimal low complexity detector and that can be implemented, and we can obtain very good results with the implementation of this receiver. So here we have an example of a system with 4 subcarriers. Specifically, here we have 1, 2, 3, 4 subcarriers that can accommodate 6 users. 1, 2, 3, 4, 5, 6 users. Okay, this means an overloaded system. Additionally, note that not all users transmit on all subcarriers. For instance, user 1 transmits in the first and second subcarrier, user 3 transmits in the first and third subcarriers, and so on. Okay. And what is the idea? In this context, complex values created from these mother constellations are obtained. And the idea here is that these complex values and these complex numbers are transmitted in different subcarriers. Okay. For this reason, this is a co-domain technique, because we're creating a kind of code for transmitting the different users, and the idea is to recover the bits that this user transmitted on the receiver. Okay. Well, and for instance, user 3 transmit this symbol here and this symbol here if he transmits, for instance, the bit 0, 1, 0, 0. Okay. And then the idea is that all signals are summed. Okay, and this information is received, and from this information received in 4 subcarriers, we want to decode information of all the 6 users. Okay, and it is possible. If you want to learn some additional aspects about sparse code multiple access, in this moment the time is short, but if you want to download some simulations in MATLAB or some papers related with this, you can scan this QR code where I have shared for you some documents and some simulations related with non-orthogonal multiple access. Okay. Well, so at the end of the previous year, we propose a strategy for enhanced physical layer security, which was accepted in the EEE Transactions on Vehicular Technology paper, a journal. And I'm going to discuss you now some details about this proposal. Okay, so let us consider the uplink of an sparse code multiple access system where we have J users. Okay, here we have 1 user, 2, 3 J users. Okay, a legitimate base station. Okay, which is named as Bob, and a spying or eavesdropper base station that is attempting to decode information from these J users. Okay, so in the analyzed system, we consider a fading channel of the kappa mu type, which is a statistical model that aligns well with the random attenuation of the Wire channel in millimeter wave propagation environments. Okay, this is the system model that we have considered. And basically, as I mentioned earlier, the generation of codebooks or multidimensional constellations is derived from the rotations of multidimensional MQAM constellations. This process is carried out using orthonormal matrices. Here we have, for instance, a matrix for 4 dimensions, okay? And this matrix depends on the rotations parameters that we have here, lambda 2 and lambda 4, okay? So the proper selection of these parameters determines if the system is going to perform well or not, okay? It's important to indicate that not all rotation angles necessarily ensure optimal performance, and this was the center of our work, okay? So in the paper that proposed this technique called signal space diversity, in 1998, the authors proposed the optimal rotation angles for Rayleigh fading. Okay. However, these analyses had not been conducted for generalized fading channels. For instance, the kappa mu fading channel that we have considered in our work. So, in our work, we derived a metric, this metric here, that enables the determination of the base rotation matrices, or equivalently the base rotation parameters, to ensure the optimal performance of the sparse code multiple access systems. Okay, so the idea is to obtain the best rotation parameters, specifically lambda 2, lambda 4. What are the best rotation parameters? And this metric this is one of the main contribution of this work, that we determined that this metric depends on the fading channel parameters and the rotation parameters. It is not unique, okay? And in this figure here, we have highlighted in red the regions where we obtained the best rotation parameters. Specifically, we obtained the value of this matrix L as a function of lambda 2 and lambda 4. And we have determined that in these regions, okay, we obtain the best rotation parameters in order to create these mother constellations that ensure the best performance for the sparse code multiple access system, okay? Well, so what is the idea here? Each user may have different rotations parameters because their channel experience independent fading. And here we have an idea to create an algorithm to ensure security. Okay, now with these tools at hand, we can generate small databases with the best rotation parameters for each user. So if user terminals have sufficient computational capability, okay, this information can be computed at the user terminals, okay, and at the base station, because the user terminals and the base station knows the information about the channel, okay? So it's important to note that the parameters for the channel between the users and the eavesdropper are different, okay? Here we have that the channel affecting this link, for instance, is different or is independent for the fading channel affecting this link, okay? So, therefore, even if the eavesdropper was aware of our metric, it could not determine the same rotation parameters as those for the link between the users and the legitimate base station, because remember that the rotation parameters are dependent on the fading channel affecting the link. Okay, so however, it's important to take into account that errors in channel estimation can lead to different rotation parameters, but we have also proposed the strategies to minimize this error. Okay, however, we can consider the worst case scenario in which user terminals lack sufficient computational capability or capacity, like in the case or in Internet of Things devices, okay? In this case, the base station determines the best rotation parameters and transmits them to the users, okay? So let us assume that the eavesdropper intercepts this information, okay? The eavesdropper obtained this database with the best rotation parameters. So the question now is, how do we protect the information transmitted by the users, okay? And the idea was the next. So we can proceed with the use of a unique secret key that is known only to the base station and its user. And this key is generated based on the estimation of the wireless channel, okay? Specifically on the fading channel, okay? So this fading channel has unique characteristics for the link between each user and the base station. In particular, we use the channel phase because it exhibits significantly differently statistical behaviors for each user. Okay, so for this reason, we use the phase of the channel. So as an example, this figure here, okay, this figure here displays the probability density function of the phases for 4 different users, okay, based on the parameters of the fading channel. Here we have changed the kappa and mi parameters of the fading channel, and here we can observe that they are quite distinct, further complicating the eavesdropper task, okay, because remember, the secret key is created based on the random phase created by the fading channel. Okay, then these random phases are used as initial parameters to create chaotic sequences, and from these sequences we can establish the rotation parameters that both each user and the base station should use for encoding and decoding process. So basically, we can generate chaotic sequences with various numbers between 0 and 1, and from this we can create a bit of sequences that results in a decimal number, indicating which rotation parameter to select from the database. Okay, this prevents eavesdropper from determining the rotation parameters used in the transmitting event. Okay. Well, to conclude, let me present you some numerical results. So initially, we are going to analyze what happens solely with the bit error probability, okay, of the legitimate users, okay, when using the rotation parameters obtained with our metric. Okay, so these figures here illustrate the average error probability as a function of the signal-to-noise radio, the normalized signal-to-noise radio. And if we compare in the figure of the left, we have employed the optimal rotation parameters that we have obtained with our proposal, and in the right side we have used non-optimal rotation parameters. Specifically, here we have used the rotation parameters that Viterbo von Boutrous found for Rayleigh fading. Okay, and if we compare both figures, we can observe that we obtain a lower average error probability for this SMA system when our rotation parameters are used. Okay, this is the first result and the first contribution. So it means that our metric is working well. Okay, and here finally we have the average error probability for both the eavesdropper and the sparse code multiple access system frame. Okay, meaning in other words, this frame is the average of the average error probability for all legitimate users. Okay, so once again, here we have the average error probability as a function of the normalized signal-to-noise radio, and we have considered different levels of error in the channel estimation. Here, for instance, in the left image, there is no error in channel estimation, while in the right side we have a higher level of error of estimation in the fading channel. So the issue with the channel estimation error is that the legitimate base station and the user's terminals may estimate different phases or parameters of the fading channel, which can lead to the use of a different rotation parameter in the encoding and decoding processes in the sparse code multiple access system, which is not good. Okay, so However, we have proposed some strategies to combat this, and the results indicate that the eavesdropper here, this is the average bit error probability of the eavesdropper. The eavesdropper has an extremely high bit error probability, implying that this device cannot decode information of any user. Okay. Furthermore, the proposed strategy is quite robust against channel estimation, and noted that there is no significant difference in performance between the results in this figure here and this figure here, and we are obtaining a good performance for the legitimate users, and the eavesdropper cannot decode the information. Okay. Well, in summary, non-orthogonal multiple access emerges as a promising solution for Internet of Things networks, and it aligns well with the objectives and the key performance indicators of 5G and 6G by enhancing connectivity, increasing throughput, offering flexible resource allocation, and optimizing spectrum utilization. Okay, so the idea here in our proposal was to create different codebooks that are unknown to the eavesdropper, and the generation of these codebooks ensure a good system performance for the users, for the trusted users, but the idea is that the eavesdropper cannot decode all the information. Okay, that's all. Thank you so much for your attention.
Thank you so much, Dr. Carvajal. If someone is having some question, please. Yeah, we have one question. What are the computational complexity analysis to execute this security mechanism, especially considering capacity-limited devices?
Yes, this is the main idea behind this proposal, because remember that Internet of Things devices don't have a high computational complexity. So the idea here, as I said, if the final devices has a high computational complexity, they can calculate this using this simple metric that we obtained. However, if they don't have enough computational complexity, we can do that the base station can calculate this metric and obtain the base rotation parameters, which is not complicated, okay? But in the case that the final devices cannot calculate these metrics, the base station can calculate them easily, and then the base station can transmit this information to the final devices, to the user terminals, and then using our proposal, both the base station and the terminal users can establish which one of the parameters must be used in order to ensure the best performance, and this information is changed, after several transmissions in order to make the life of the eavesdropper more difficult.
Paola, you unmute, I think.
Yeah.
Sorry, thank you, Bart. I have one question. How about the vulnerability? No, what types of physical layer attacks are most relevant in the context of CDNOMA that you have talked?
Okay. In the case of non-orthogonal multiple access, we have different problems. One of the problems is that the radio resource is shared by different users. Okay, for instance, let us consider power domain NOMA, non-orthogonal multiple access. Here we have the information of 2 or 3 users is transmitted in the same radio resource. And the problem is that if we have one untrusted user in this group of users, this user can hear the information that is transmitted to the other users. Okay, and for this reason, we need some additional strategies to complement traditional cybersecurity algorithms that are more simpler, that can be used for simple devices like these devices of Internet of Things. So this is one example of this kind of attacks.
Okay, and I don't know. Another question that is going by mind. In which real-world application or network scenarios is secure CD-NOMA or is more beneficial?
Okay, for now, it's just a proposal. The idea is to ensure that future 6G networks can support 1,000 devices per square per cubic meter specifically, and a scenario where we can this number of devices maybe is related with industrial scenarios. Okay, maybe in our home, in our house, we don't have this number of devices, but I think that these proposals related with non-orthogonal multiple access and this idea of massive communications is very useful in industrial environments.
Okay, thank you so much. Henry, I don't know if someone is having another question. Yeah.
I think there is a question in the chat.
In the chat. Oh, okay. Let me see. Okay, see, it's another one. Please, could you mention some project to apply for our country or city with this technology?
Okay, intelligent cities. I think this is a good alternative where we have that some devices that use low bit rates and they do not require a very low latency. Maybe are an option
exactly
for this.
Yeah. Thank you so much. I don't know, Bart, if you want to add something.
No, I think this was a very interesting presentation. It seems that some of these results you were showing in the diagrams are coming from perhaps your recent publications. So, I mean, everyone has access to Scholar, but I think it would be nice to leave some contact details or share some contact details, Paola, especially with the rest of the consortium. So here I'm referring to Ensure 6G Consortium because, of course, we will be doing some cross collaboration. Yes.
Okay, I forget to show this slide. Here you have my personal website and you have my email. So if you need or you have some another additional question, or if we can work together in some project related with this technology, please write me.
Yes. Yeah, so thanks for this, and I will be definitely checking out the profile because some of this research stuff is new to me, relatively new. So that'd be great. And I guess we now have a lot of people, and keeping up this academic spirit. Perhaps some of the new joiners don't know, but as Paola mentioned at the beginning, this is a collaborative project between now 14 different countries. There are a total of 343 exchanges planned over the next 4 years. So it's extremely likely that people you see here today online, they will be actually visiting your facilities at some stage over the next few years. And vice versa. I'm sure there will be people from UDLA coming over to Europe, and you're very welcome to visit all of our partners. So yeah, I mean, I think exchanging this contact details and research articles, I think it's extremely valuable. For this, I think we will also do a follow-up, maybe like a blog post where we can link also some of your emails and have be able to extend your network beyond what you currently have. But yeah, I don't have technical questions. I will definitely deep dive into your work, which seems to be very relevant and very interesting. And especially that one last comment. There are not a lot of because the last questions were about the physical layer specifically. there is a lot that needs to be done in the physical layer, and not a lot of companies or universities that do work in the physical layer. There was a clear shift towards AI, explainability of AI, but there is still we're lacking for partners, for example, that work specifically in the physical layer, and then also executing tests and doing validations of these research ideas is also not straightforward, because it's not a simple Python scripting that you can do. It's using things like, for example, OpenRes. We work with reflective intelligence surfaces, and this is actually a very physical test bed that needs to be distributed. The 5G test beds themselves are quite distributed when it comes to the physical distribution. And lastly, I just want to say that if you want to be publishable lately, you should execute tests in real physical environments, because there is a lot of work. It's quite saturated in the research world. People working with different data sets and doing theoretical / semi real life testing. Now we need things like 5G and future beyond 5G testbeds. Just as a bit of advertising, in UCD Nets Lab, we have a 5G ORAN testbed that is not extremely open, but it is very open. So all the data sets that we generate with real-time data, the actual telecommunication like data, is open to the outside world and to the every researcher possible, unlike with the actual telecommunication companies. So we work with some great teleco companies, but when we ask them for data, they just turn around and walk their own way because they don't want to share anything, and that is understandable. They deal with real users. We deal with emulated users, or the devices that generate traffic that is not sensitive, but it still generates data. So that's my observation from the last, I think, couple of months of trying to figure out what is going on in this 5G publishing space. So that is, I think, something you can look into. I can also link in the blog post the 5G ORAN testbed that I was mentioning just now, and you are welcome to use it. Okay, thanks, Paola. That's my last comment, and we can go back. I'm not too sure what's left in the agenda.